Welcome to After Hours Engineering, Episode 3, RISC-V Softcore. In this episode, we begin looking at the RISC-V ISA, or more specifically, the RV32I base instruction set. This ISA is split between two volumes, the instruction set and the privileged architecture. However, it would take us hours to deep dive into every aspect of the manual. So to save time, I'll cover only the key areas that are important to the implementation, and as such I'm going to assume the following. 1. Understanding signed and unsigned binary numbers, including 2's complement. Basic concepts of assembly language programming and Boolean logic and arithmetic. In addition, there are a few concepts I won't be addressing or even implementing completely. Instruction address misalignment exceptions, and system instructions, the eBreak and the eCall, although the eBreak will be present and used mostly just to halt the processor. It's not a true trap exception. So with that in mind, let's begin with the 4 core instructions, the R, I, S, and U. As we explore the instructions, it would be helpful to have 2 other sources, the reference sheet and the RISC-V reader. These provide additional information as well as different perspectives of the ISA. So with those 2 in hand, it's easier to start with the R, I, S, and U set because there's no requirement to bit swizzle in order to place a produced value into any of the immediate bit positions. The RISC-V is no exception. It adjusts its bit positions in order to optimize the hardware and software sometimes. So, looking at Figure 2, a pattern emerges in that the instructions are very columnar. RD is always in the RD column and is always in the same bit positions. RS1 is in the same column, RS2, and the opcode. This is a very familiar and reoccurring theme within the RISC-V ISA. But there is something else we need to note, and that is down here in the text portion. It's very important to pay attention to this immediate value being produced. And this is going to come in to play when we start exploring the B and the J instruction types. With that in mind, we begin with the R-type instructions. These are the register-to-register type instructions, meaning that everything is a register in this instruction, the destination register and 2 operands, including a function specifier for adding, subtracting, anding, shift-right arithmetic as an example, and then a further specifier to differentiate between subtraction and shifting. Let's take a look at what one is put together as. We have the opcode for the add. In this example, it's an add. We have the destination is x3, so that's a 3. Our function is 0 because it's an add. And our 2 operands, x1 and x2, and our function 7 is 0 because it's an add. If we were to break this up nibbles and then reassemble them, this is the machine code for an add where we're setting our destination register x3 equal to the sum of x1 and x2. Easy enough. The description for each one of these registers looks like this. It's the destination equals RS1 some operand RS2, and they are listed all here in the reference guide. Some are most significant byte extended or sign extended in this case, or 0 extended in this case. These are the 2 unusual ones where we're just setting the destination register to a 1 or a 0 based on a single function, which is the less than operator. Next are the I-type instructions, or immediate instructions. Just as we had with the register types, we have an immediate variation on those where you can add, subtract, or anything you want as long as one of the operands is in this immediate position. The other is in this RS1 position, and then of course we have a destination we're applying it. As an example, we have the ADDI, which is going to add this immediate value to this register right here and put it in the destination register. And this is the same listing that we had above, but now it's adding in an immediate instead of a second register to it. There is also another immediate, the jump and link register instruction, which takes a base address, adds an offset, the offset itself being the immediate value in the instruction, and puts the return address in the destination register. Again, it's very columnar. You have the RD in the same exact position that you have in all the other instructions. RS1 is also in the same position. And in this case, the immediate is in the same position as any of the adds, subtracts, and logical instructions. There is also an additional I instruction, the E-break and E-call. And in this case, there's no particular thing that you're placing in there because the values are fixed in what they are. They're always zeros in this case. It's the opcode that differentiates between the two, and the immediate would have a 1 or a 0 in it. Next are the I-type loads and the S-type store instructions. For the I load, we have an opcode as usual. We have a destination register that we're going to load with a value from memory. We specify the size of the thing that we're loading in this case. It could be a byte, a half word, or a word. A base address that allows us for relative addressing, and then an immediate value. So if we come down here to the load word, we can see here's our base register. The offset will add to that, and then the destination that will be loaded with the value that's at that memory address. The store opcode is structured very similar, only instead of a destination register, we have an immediate value that's taking part here. So the way this works is we have our base address, the RS1 register, and an offset that will add to that, and then RS2 specifies the source of where the data is coming from. So RS2 is going to have our value that we're going to store into memory, and this specifies where we will be storing it. Now the key point to know in this is that a thing called endianness, how data is loaded or stored into memory, and it only means something during that process. And so there's a section inside the manual that specifically talks to little or big endian. And here's an example of the two. In the little endian system, the least significant byte in our instruction, if you will, is stored in the lowest memory address, and then as we move along we eventually reach the highest byte in the instruction register, as an example here, and it's stored at the highest address. Whereas on big endian, the lowest byte in our instruction register is stored at the highest address, and so we start from A and we go down to A plus 3. Now for my system, I'm going to be using big endian systems, and that's not that common. It's more common to do little endian, but I chose big endian so that my memory model looks identical to the instruction register. Had I have chosen to use a little endian model, I would have reversed all my bytes, and then as I'm loading them into the instruct register, I put them back into the order that my processor expects them to be in, which is big endian. So again, I went with the big endian in memory. And again, it's important to stress that the endianness only means something during loading and storing. For example, this is the break instruction, and it's still the break instruction no matter what you do to it. It always will come out to be in this order in your processor, in your soft core. So that's the load and the store. Lastly, we have the U-type instruction. We have two of them, the load upper immediate and the add upper immediate to PC. One is for building a 32-bit constant, and the other is for building PC relative addresses so that you can span the entire 32-bit address space. The top one, we take the top 20 bits, which is the largest of the immediates, and we load it into the upper section of the destination register and then add in zeros for the rest of them. And the other one again is just for loading the destination register with an immediate value. And you can see how the descriptions show it as a shift, but you don't have to do it as a shift. You can do it using the concatenation operator. So that's it. That's the last of the R, I, S, and U instructions. And there you have it, the core instruction set, R, I, S, and U. which includes the arithmetic and load and store instructions. However, there are still two instruction types that will complete the Turing model, the branch and the jump instructions, and we'll cover those in the next episode. So until next time, peace!